Hey, this is Joe, and in the next couple of videos we're going to be building an AC/DC data logger. What we have here is a AC/DC clamp meter, and it has a selectable range of 0 to 40 and 0 to 400 amps. We can then use this device to measure current without disconnecting any of the wires in the circuit. We have a 30-pin header board with screw connectors. We can then take our ESP8266 32-bit microcontroller and we can put it on that board. The nice thing about this microcontroller is it has a built-in USB port and it has a built-in Wi-Fi transmitter receiver. We also have a 16-bit 4-channel analog to digital converter. We have a little terminal block. We have a project box, some 4-pin Grove connectors, and some extensions here for the clamp meter. And what we're going to be doing in the next several videos is we're going to be building this data logger. And for those of you that have some experience, you can follow along in the first video or so. And then I'm going to do another video which, if you have no experience working with microcontrollers or basic electronics, I'm going to take you and walk you through step by step on how to set up and program the microcontroller. I'm going to show you how to set up your environment on your computer, whether it's Windows, Apple, or Linux. The development platform that we're using can run on all different platforms. It's a free package, so it doesn't cost you anything. I'm going to develop all of the code for this project, and I'm going to publish it out to a public available repository called GitHub, and you can simply go in and download the program and upload it to your data logger. And we're going to do several different projects here. We're going to, in one of the projects, we're going to use the serial port or the USB port to send serial data to the computer that this data logger is connected to, and then you can capture that data, that current being logged, to a text file, and then you can take a program such as Excel and you can graph it. You can then analyze the data. Another scenario we're going to do is Google has a cloud-based package called Firebase, and as part of that development environment there is a database. So we're going to take the Wi-Fi chip here and we're going to write things out through your Wi-Fi connection. It's going to then make a connection to Google Firebase and record all that information in a database, so we can then go online anywhere in the world and we can access our data, and then we can again use Excel to graph it out, analyze the data, whatever you want to do. The third scenario we're possibly going to do is also to take the information, send it out over Wi-Fi to an Android or Apple smartphone, and then you're going to be able to let's say remotely access the data logging and access that through your phone. I don't have an iPhone, but I do have an Android device, so we're going to actually develop it using the Android device, but the process will be very similar to if you have an iPhone. So let's go ahead and get started. Again, I'm going to do several videos, and in one of the videos, if you have no experience working with microcontrollers, basic electronics, I'm going to walk you through everything. I'm going to write all the code for you so you can download the code, and using my instructions in the tutorial video, show you how to upload and get everything working on the data logger if you decide to build this yourself. So let's get started. One thing I want to mention is this blue mat you see here is an anti-static mat, and this is grounded to the ground side of an electrical outlet. So anytime you're working with electronic components, especially microcontrollers, you want to make sure that you have an anti-static mat, and that will prevent any possible problems with damaging your electronic components. So you can pick these up on Amazon very inexpensively, and you want to make sure you take the lead and ground it to the grounding plug which is your center screw there on your outlet, and that way all of your devices will be protected from static discharge problems. First thing we're going to do is we're going to take our 30-pin connector, and we're going to take our microcontroller here, and you want to look at the writing on the pins, and if you'll notice, the writing on the header also has the same writing, so you want to match up. When you plug in these pins, you want to make sure that you get the microcontroller mounted in the proper orientation, which match the writing on the header pins as well. This will act as a way for us to connect our outside devices like the meter and the analog to digital board to the microcontroller very easily without having to do any soldering whatsoever. In fact, this whole project we can do without any soldering at all. So it makes it a little easier on the folks that don't have all of the tooling that you need if you have to solder, or the skills to use a soldering iron properly. We've taken the microcontroller and we've lined up the pins the proper way. You can note that there's an A0 here, and there's an A0 on the board, so we'll make sure that the pins from the microcontroller are properly mounted. Another interesting feature of this microcontroller is it has a built-in display. So part of our development process will be to write the current that we're reading and display it to this display. So as you're watching, when you first set up your data logger, you can actually see what the current readings are. More importantly, though, we're going to write out, let's say we want to capture some current information over a period of time. That's the whole point of a data logger. We can run this for 24 hours and every minute capture a current reading. So let's say we're trying to power a refrigerator off of DC. This would be like in an RV situation. You want to be able to calculate your solar or your current usage so you can spec out your solar panels properly. You want to, let's say over a period of 8 hours or 24 hours, you want to measure how much current your refrigerator is actually using, because the way a refrigerator works is it cools it down and then it shuts down for a period of time based on your thermostat, and then it comes on again. So you're not going to get a constant amperage draw. You're going to get a period of time where the amperage draw will spike up a little bit while it's cooling down, and then the refrigerator compressor will shut down, and your use of current will be little to no current. So we want to average this out over time, so when we're speccing out our solar panels, we can get an accurate indication of how much energy we need to store in our RV battery banks. So here's our board mounted. We have our display here, and we're going to now start making some connections and wiring in the analog to digital converter. We have a terminal block here for the leads of the clamp meter. We're going to be drilling some holes in our project case. We have a board inside of the project box which we're going to drill some holes, and we're going to mount our electronic components to the board in the project case, so everything will be neatly organized and laid out. We want to take all of our components and we want to lay them out on the project box board, and then we're going to mark these with a felt tip marker, and then we're going to go out and drill some holes to mount these components to this board, and then we can take the board and put it in the project case. Before we do that, we'll wire it all up. So let's go ahead and get a felt tip marker, mark these, then we'll drill the holes. Then we can go ahead and take mounting hardware. They have some little standoffs and nuts and bolts, so we can go ahead and mount all of the components to the board. Then we can go ahead and wire the board. We picked up a box of standoff spacers, screws, and nuts on Amazon. All of the parts that I purchased will be listed in the description. They were all purchased on Amazon, As you see here, we have a standoff right here, and if you flip it upside down, you'll see that there's a little screw there. So all we have to do now is to take our standoffs and put them in the screws holes, and then we can mount our circuit board to the piece of plastic here. And the same thing with the analog to digital converter and the terminal strip. So let's go ahead and get all these mounted to the gray piece of plastic here. This was also purchased on Amazon. As you can see, we have all 4 standoffs mounted, and the standoff is either has a male thread on one end or a female thread on both ends, and that's what these are right here. The nice thing is then you put a screw in on the bottom, and then you can mount your circuit board on top of the standoffs with the thread holes, and then you can simply take your screws and mount the circuit board to the standoff. So it's a nice way to mount circuit boards in preparation of putting them in a project box. So we're going to go ahead and finish the microcontroller and header board. We have the 2 standoffs now for the analog to digital converter board, and they're going to go like that. Notice there's only 2 screw holes at the top. There's none on the bottom. So we're just going to fasten those just like that. We have our plastic mounting board inside of the plastic project box. What we'll do is we will either put some screws, drill some holes, put some screws in this plastic board and screw them down, or we'll just do some hot gluing and mount that there. But we're ready now to do our wiring. We've taken a small serrated knife and we've trimmed off some of the insulation portion of the cap. So now we can take and we can have the capability now of plugging in our leads to the extensions. Now what we're going to do is we're going to cut off the ends of the extension on the other side, strip the wire and run it through the through wall connectors, and then we'll crimp on those ring terminals, and then we can mount them to the terminal block here. We're going to take these Grove connectors. What they are is a 4-wire 4-pin connector. If you purchase the A to D board, the Switch Dock Labs, they put Grove connectors on the printed circuit board. It makes it really nice. You can just then insert the connector, and then you can wire this up to the screw terminals between the microcontroller and the terminal block. So the first connector here on the left is an analog input, and it's labeled A0. There's A0, A1, A2, and A3. These 4 connectors are to take analog signals from external devices such as our current clamp meter. You can also get voltage sensors, temperature sensors, humidity sensors, and which are all analog, and they get wired into the 4 different channels of this analog to digital converter. And then the purpose of this board is to take the analog signals and then convert them to a digital or a binary signal, which basically consists of a bunch of zeros and ones. And that's the whole purpose of this board. Now this 5th connector right here is the interface that communicates between this board and the microcontroller. Just like on your computer, if you want to attach a printer or a scanner or something to your computer, you have to install a software driver, and the software driver communicates with your operating system. and that allows you to interface to the external device, such as your printer or your hand scanner or whatever you happen to be connecting to your PC or a Mac or Linux box, whatever. Same way on a microcontroller. If you want a microcontroller to communicate to an external device, such as our current clamp meter, we have to bring that signal in through a special type of interface. And there are several different types of interfaces that this microcomputer or microcontroller supports. And one of them that we're going to be using is called I²C. It's basically an I, the number 2, and the C. And what that is a communications interface that allows you to communicate between this analog to digital board over to the microcontroller. And it takes 4 wires. It takes a ground connector, either a 3 volt or a 5 volt voltage, and then it has it has a primary signal and a secondary signal. And on our particular clamp meter, we have 2 wires. So one of them is a primary or positive signal. The other is a secondary or negative signal. And that's how we're going to use this Grove connector to tie in from the clamp meter through the terminal strip here and into the A to D converter. So the wires that we have a yellow wire, a white wire, a black wire, and a red wire. Of course, we know that red is positive, black is ground, and in the particular case of our A to D board here, the yellow wire is the positive signal or primary signal coming from the current meter or the current sensor, and the white wire is the negative or secondary signal. And those 4 wires will then give us the voltage and the ground and the primary and secondary signal coming from the current meter into the analog to digital board here. And then those wires are then routed over to the microcontroller side using the I²C interface. So let's go ahead and wire those wires up now. We have the positive lead, which is the yellow or primary wire, coming from the positive side of the clamp meter, going to the yellow pin on A0, which is the analog 0 connector. We have the white wire, which is the secondary or negative wire, going into the second, and these 2 are now connected to the terminal block here. The external wires from the clamp meter are going to go positive and negative here, and right at the very end we'll connect those in. Now we can take the red and black, and in this particular case this board is operating at 3 volts. So on this side of the screw terminal section there is a 3 volt connector and a ground connecting pin here, or screw terminal. We're going to take and we're going to strip the wires, and we're going to tie them into the ground and the 3 volt terminal on the microcontroller side. Now we've taken the red and black wire from the A0 connector, and we have the red going to the 3 volt pin, and we have the black wire going to the ground pin on the microcontroller side. So now that is wired up. Now from the I²C connector we have 4 wires, and if you look, we have the yellow wire on the clock screw pin, that is D1. The white wire is going over to the data terminal, which is D2, and then all we have to do now is route the black wire to the ground, the red wire to the 3 volt pins on this side of the header board. So let's go ahead and do that. Then all we have to do is drill a hole in the project case for the USB connector right there, and then we're ready to start testing with the board. It's very simple to wire up. We have the leads crimped on and ready to be screwed into the terminal block. When you're positioning your terminal block, make sure you have enough cable length so you'll be able to tie directly in to the terminal block. Otherwise, you're going to have to extend your wires from these leads. Either that or buy slightly longer leads. I bought the shorter ones, and I made sure that this terminal block was in a good position to reach. Now I can then screw these down, and on the other side we'll put the leads that are actually going to go to the analog to digital converter board. Here we're looking at the side of the clamp meter, and there's a selector switch. The clamp meter has two ranges. We have a 0 to 40 amp range, and we have a 0 to 400 amp range. And depending on which position the switch is in, we have, if it's in the 40 amp position, you have a 10 millivolt reading for every amp. And in the 400 amp range, that's from 0 to 400 amps, you have a 1 millivolt per amp range. So when we write the code on the microcontroller, we're going to have to take this into consideration. So I've done some testing, and I've come up with proper multipliers so that when we are taking our readings, we can apply that multiplier to either the 40 amp position or the 400 amp position, and that way we'll get an accurate reading. Now, in order to get these to work, you'll just have to make a minor code change. I do this in the form of a variable, so you just change the variable depending on what range you want to read, and then you just recompile and upload the code to your microcontroller. So when we get actually into looking at the code, I'll point this out to you and show you how we're going to make our compensations for the different millivolts per amp readings. In order to get accurate measurements with your clamp-on meter, make sure you first turn it on, and with no wires in the clamp, then hold and press the 0 button for about a second or two, and that will zero out the clamp meter readings. If you don't do this, more than likely you'll get erroneous readings. I've seen it where the voltage goes negative or the voltage is way off. So again, make sure you calibrate this with the clamp meter on and no current flowing through the clamp portion of the meter. I have a power supply set up here delivering 12 volts. Currently we have a load at 1.041 amps, and if I move down here, you'll notice here is my variable load, and we're getting 11.8 volts at 1.04 amps. And then if we move over here, you'll see there is the current meter, and it is clamped on to the red lead to the variable load. And then if we pan over here, you notice on the microcontroller we have 1.05 amps on the current meter. So if we come over here and we bump our current up, let's go up to 2 amps, there we have 2.1 amps there. On the load we have it's fluctuating a little bit between 2.08 and 2.1. And then if we pan over to the meter on the microcontroller, we're sitting at 2.175. There will be a little bit of variation between all the readings. We don't know what the accurate source is, so I'm using 3 sources here. But as you can see, we are measuring current, and I have the interval set at every 5 seconds. So every 5 seconds we get a new reading. Let's now go over and take a look at the serial port on the computer. What we have here is a piece of software called the Arduino IDE. It's a development environment for microcontrollers based on the Arduino, and we're using the ESP8266, which is a 32-bit microcontroller, and you can program that using the Arduino IDE. What you see here on the screen is we have the serial monitor running, and every 5 seconds we're capturing current data from my variable load device. Let me change the current here for you, and let's go up. Notice now we're reading 2.23 amps, so I varied that, and this is making a reading taking a reading every 5 seconds. And again, this is adjustable. You can go in and configure this in the program. But as you see here, we are capturing real-time data from the variable load and power supply using the current clamp through the data logger that we just built. So if I close this program now, and what I'm going to do now is load another communications program referred to as PuTTY. And in PuTTY, what you can do is we'll go down to serial. We'll choose the right COM port, which the microcontroller is running on COM 5. We're going to change the speed of the port to match what the microcontroller is transmitting the signal at. We're going to go over and we're going to create a log file. And so now we've saved the putty.log file. And what we're going to do now is go over, make sure everything is set properly. And we're going to go up to session, and we're going to select serial, and we're going to select raw data. And what we're going to do now is, as you see here on the screen, we're capturing raw data to a serial capture program. And this is coming from the microcontroller. And let me adjust the current again. And I bumped the current up to 3.041 amps. So as you see, we got an immediate read after a 5-second sampling rate here. I'm taking a reading every 5 seconds. So what we're going to do is we're going to let this run for a while, and I want to capture a bunch of data. Then we'll come back and I will show you how to graph this out in Excel. So I'll capture some data off camera, and then we'll come back and I'll show you how we're going to graph that data out in a spreadsheet program such as Excel. After we've collected some data for a little bit, out here under the videos data logger folder, I have a putty.log file. What we're going to do is we're going to go over and load a blank spreadsheet, and we're going to open our putty.log file. And then what we're going to do is we're going to import that log file into Excel. And then we're going to get rid of the title. Now we're going to select the column that we want to graph. Our graph. And we're going to select a line graph. And as you can see here, we have now a line graph of our current increasing up. So the nice thing here is, again, if I'm capturing current from a device, let's say such as a refrigerator, over a period of, let's say 24 hours, I can now see what the current usage is going to be on that device, in this case a particular a refrigerator. So that's how the data logger will work. So at this point, what I'm going to do is end the video. This will give you enough information that if you want to build your own data logger for current readings, AC or DC, then in the next video, what I'm going to do is we're going to show you how to set up your own environment on your computer, and how to build the actual application, how to upload that program to your microcontroller. What we'll do at that point is we'll analyze the code and try to break it down into plain English so that everyone can understand what's going on. Then in a later video, we're then going to take a look at doing a little bit more sophisticated things like uploading the captured data from the microcontroller using Wi-Fi, and uploading that data into Google Firebase, which again has a cloud-based database. So no matter where we're at, no matter what location, we can then access that captured data from the logger right from the internet. So hope you enjoyed this video, and we'll see you next time.